Okay, so we've got our problem set up here. In mice, black fur is dominant to white fur. If a heterozygous mother mates with a white father, what genotype and phenotype ratios would be expected among the offspring? We are using big F, little f for fur. So, the first thing we have to do is write down the mother and father's genotypes. So we're going to do that over here. And the mother's genotype would be what? So it says that mother is heterozygous. She is big F, little f. Okay, now dad, it says, is white. What do we know about white fur in these mice? It's recessive. So what does his genotype have to be? Little f, little f. Okay, once we have the genotypes for mom and dad written down, then we can do a Punnett square. And this is the easy part. So, big F, little f, little f, little f. Okay, go ahead and do your square. Okay, so we have a Punnett square completed. And now we need to get our genotype and phenotype ratios recorded. Okay, so how many capital F's do we have? None. There are none of those. And what about heterozygous individuals? We got 2, and we have 2 homozygous recessive. So what's our overall ratio in the offspring? 2 to 2. And we can simplify that. We can say it's 1 to 1. Either one is oh, geez, what did I just do? I wrote 2 to 1. So it's, yeah, 2 to 2 or 1 to 1. And how many black-furred offspring would we expect? 2. How many white-furred offspring? 2. So what's the ratio? 2 to 2. Or again, 1 to 1. And if we wanted to put it in percentage odds, we would expect about what percent of their offspring to have black fur? 50%. So, the key to doing any kind of word problems with these is just writing down the genotype of both parents. As long as you do that step, then the rest is easy. It's what you've already done. But it's getting used to going from the verbal description to the genotype. Let's do one of these with a word problem that involves, we started to talk a little bit on Friday about disease traits and about sex-linked disorders. So let's do one with a disease, and let's do one with a sex-linked trait. How many of you remember anything about sex-linked traits? Okay, we're going to review on those. Okay, let's set up another problem. Okay, so we're dealing with sickle cell anemia. This is one we had started to talk about a little bit on Friday. Very common among Americans of African ancestry. So the allele for sickle cell anemia is recessive. We're using a small r. We would use the big R for the usual red blood cell allele. If a mother with sickle cell anemia reproduces with a non-carrier father, whoops, let me get rid of that. A non-carrier father, what genotype and phenotype ratios would be expected in the offspring? Okay, so a mother with sickle cell and a father who's not a carrier. So our options, well, what is mom's genotype? If she has sickle cell, what's her genotype? Does it have to be? It has to be little r, little r. It's recessive, so you're right.
Wouldn't there be like something in there?
Okay, so if mom has sickle cell, she is little r, little r. Dad, we are told, is not a carrier. He knows this, so we're guessing that he's been tested. He is big R, big R. Okay, so what kind of genotype and phenotype ratios would we expect in their offspring? Now it's just down to doing a Punnett square. So we have our Punnett square set up. Okay, so we have our Punnett square done. How many big R's do we have?
Zero.
We got none. And then these big R, little r's, how many of those do we have? There we have 4. How many little r, little r's? None. So what's our ratio? It's 4-0. Okay. How many of their offspring are sickle cell affected? None. Not a single offspring of theirs would we expect to see affected. How many of their offspring are carriers? Yeah, every single one of their offspring. And are there any offspring that aren't carriers? No, we just said that they're all carriers. So the ratio is 4-0. So for this couple, knowing that she's affected, they have to very seriously consider if they want to go ahead and have children biologically. Because they know that they're going to pass on, she knows she's going to pass on that sickle cell gene to every single one of her kids. Which, her kids aren't going to be affected, but her grandchildren could be. And she has to kind of consider that. The gene is not that uncommon among Africans or Americans with African ancestry. We're going to talk more about CF on Wednesday. That's one that's 1 in 20 people with European ancestry carry a CF gene. I think it's 1 in 12 Americans with African ancestry carry a sickle cell gene. So, these are real common. In this room of 20, the odds are that one of you is a carrier for CF. If we have a classroom full of African American students, if we have 12 of them, the odds are that one of them is a carrier. So these are things that are linked to your geographic, the location where your ancestors came from. We're all Americans, but our ancestors came from different parts of the planet, and these genes crop up in those locations, and we carry them along with us. So, okay, let's do one that's sex-linked. So let's do a little bit of review on sex-linked first. Sex-linked traits. Which are they are carried on sex chromosomes. Which are the sex chromosomes? X and Y. And females have which pair? XX. Males have XY. Yes. So, where are sex-linked conditions typically carried? The ones that we're talking about. They're typically on the X, and they typically affect who? Males. Because, guys, you don't have a spare copy. It's like driving down the road with no spare tire. You blow a tire, you're done. You're not driving. If you have a defective X chromosome, gentlemen, you have no spare tire. You have nothing to back that up. Okay, and we very often show these as things like X with a capital N for the usual configuration, or X with a small n for the affected condition. Okay? All right, so that's a little bit of an overview review. Now let's practice one. I'll read this while you copy. Duchenne's muscular dystrophy. That's MD for muscular dystrophy. Duchenne's muscular dystrophy is an X-linked recessive condition. So it is carried on the X chromosome, and it is recessive. If a carrier mother reproduces with an unaffected father, what genotype and phenotype ratios would we expect to see in male and female offspring? So we have to actually do the ratios here for males and females differently, because the males and females are going to be affected differently. Okay, I will let you copy. And we have here a carrier mother and an unaffected father. Let's go ahead and do the genotypes and phenotypes for mom and dad. So, what is mom's genotype with regard to this allele? We know she's XX, and she's a carrier. She's not affected. So we know she has one normal X chromosome, and we know she has one X chromosome that carries the allele for Duchenne's. What about dad?
XY.
He's XY, and his X chromosome is a normal X chromosome. Otherwise, he would probably not have survived to an age where he could reproduce. He wouldn't have lived to see kids. So now we have enough information here to do a Punnett Square. Okay, so we now have enough information to do our cross here. So we have X big N, X big N, X big N, X little n. X big N Y, X little n Y. So we're going to do our male and female genotype ratios separately. So for her female offspring, what genotypes are possible? What genotypes are possible for her female offspring? Okay, so how many of each do we show in our Punnett Square? We show one of each. And for her male offspring, X big N, Y, okay. I will finish a tutorial on this. You'll watch it on YouTube. You will have your quiz tomorrow. Okay, so the other possible genotype we see for her male offspring is X little n Y. We see one of each. So what this means is that for her female offspring, non-carriers versus carriers are a 1-to-1 ratio. So half her daughters will be expected to be carriers. For her male sons, affected or not, is also 1-to-1. So we would expect that half of her sons would be affected with Duchenne's muscular dystrophy. Okay, that's it. Quiz tomorrow.